Hello, everyone. In this video, we're going to cover the three different types of chemical bonds that are formed and are important to biological life. So, for this first part, we're going to look at the concept of the formation and function of molecules and ionic compounds depend on chemical bonding between atoms. So, in the last video, we covered how some atoms have a valence electron shell that is incomplete. And so, because of these shells being incomplete, this will create unique behaviors and characteristics for atoms and their interactions with other atoms. And so, if an valence shell is incomplete, atoms will want to bond to form a complete shell. And so, we're going to review the different attractions that are called chemical bonds. The first bond that we're going to review is covalent bonds. A covalent bond is the sharing of a pair of valence electrons by two atoms. It's important that you realize that this is a shared bond. It's shared electrons between atoms. And it's very easy to remember this because remember, sharing is caring. So sharing is covalent. Um, and so when atoms bond together in a covalent bond, the atoms are shared and they count for both atoms. So this is just showing you how two hydrogen atoms will bond together to form H2, the molecule. So a molecule consists of two or more atoms held together by a covalent bond. If it's a single covalent bond, it's called a single bond. If it's a double covalent bond, it's called a double bond. And you can actually have triple or quad-based bonding. There can be four bonds between atoms. The notation used to represent atoms bonding is called a structural formula. For example, hydrogen bonded to hydrogen represents a single bond. The single bond is displayed by the one line between the two hydrogen atoms. If it's a double bond, it will be a double line, as seen here in the two oxygen atoms. If it's triple, it's three. If it's a quad bond, it will be four. And so you can either write it as H-H to represent H2 molecule, or you can just write it in the abbreviated form, which is the molecular formula, as just H with a subscript of 2, meaning there are two hydrogen bonds. And so here's a chart showing you several different examples of covalent bonding between different atoms, and you can have your single bonds all the way up to something as complex, for example, as methane, which has four single bonds. So four single bonds with hydrogen and carbon. So covalent bonds can form between atoms of the same element or atoms of different elements. And so a compound is a combination of two or more different elements. Atoms in a molecule will attract electrons to a varying degrees. It depends on the atoms, what we call electronegativity. So electronegativity is an atom's attraction for the electrons in a covalent bond. Some atoms are more electronegative than other atoms, and this really has to depend upon the number of valence electrons that an atom has. So for example, if you're fluorine, you're missing only one electron. So you'll have a higher electronegativity. You're more likely to bond with something instead of being separated. Now, covalent bonds can form in two different ways. It can be polar or nonpolar. In a nonpolar covalent bonds, the atoms share the electron equally. There's an equal share of the electron. If it's a polar covalent bond, one atom is getting the electron for a little bit longer than the other atoms. And so this creates a electronegative uh, charge where part of the molecule is negative and part of it is partially positive. And so this creates a pole, like a thinking like a pole of a magnet, where one side is slightly positive, one side is slightly negative. The most famous polar covalent bond is seen in the water molecules. So water molecules are polar covalent bonded molecules. And because water is a polar covalent bonded molecule, it helps create some of the characteristics that are unique to water and why water is so important for biological molecules. In this diagram, you can see that the hydrogen here, the electrons for the hydrogen are more, not more attracted, I was going to say more attracted. They spend more time with the oxygen uh, atom compared to the hydrogen atom. So the oxygen atom is slightly negative compared to the hydrogens, which are slightly positive, and that creates a polar molecule. Ionic bonds have create charged um, atoms, and so they are different compared to covalent bonds in that ionic bonds are more about they don't share. It's more about I call cops and robbers based bonding, in that one will steal the electron from the other, and so they will strip the electrons from their partners. And so when they do that, they become slightly charged atoms, which we call ions. A positively charged atom is called a cation. A negatively charged ion is called an anion. And you can remember this. This is how I tell my students to remember this. Cats are positive. So cations are positive ions. Anions and cations attract each other, and this attraction to each other is the ionic bond. So this is giving you an example back to the sodium chloride, um, where sodium has one extra electron in its valence shell compared to chlorine, which is missing an electron. So chlorine will take that electron from sodium, and so chlorine will now be slightly negative and sodium will be slightly positive. And you can remember that because chlorine took that electron, so it's the robber, so it's going to be a negative. And sodium lost its electron, so it was the good person in this example. So sodium chloride is an example of a ionic bond. Now, ionic bonds create ionic compounds, which are also called salts, such as table salt is often found in nature as crystals. And so a lot of the salts or ionic compounds found in nature, when it's dry, will be in a crystalline form. But when it's exposed to water, it will very easily disassociate and dissolve in water. So sodium chloride here, table salt in nature, will form these crystalline structures based on it's just based on their chemical structure and how they like to bond together. But when exposed to water, they will dissolve. And so because of that, ionic bonds are considered a weak bond. Covalent bonds, where sharing is caring, covalent bonds are strong. They're the strongest bonds. However, if you are a biological organism, you don't want all of your molecules to be strongly bonded together. You only want the ones that really count to be strongly bonded together. If you are having molecules and you need them to do work or jobs and to undergo chemical reactions, they cannot have a strong bond. So a lot of them internal molecules are um, ionic in nature. There are several other types of weak chemical reactions, such as hydrogen bonds. A hydrogen bond will form when a hydrogen atom is covalently bonded to another electronegative atom. And so it's very common for these to form between oxygen and oxygen or nitrogen with hydrogen. Um, it is also very common in the water molecule. So water molecules will hydrogen bond together. And so that creates some of the characteristics that we see in the water molecule. In the next chapter, we're going to review all of the different characteristics and behaviors of the water molecule and why it's so important. Another form of interaction is van der Waal interactions. If the electrons are not evenly distributed, they may accumulate by chance in one part of the molecule. And so van der Waal interactions are attractions between molecules that are close together as a result of these charges. So the best example that I know of, and it's used and studied quite intensely, is the gecko toe hair. So geckos, their toes, have all these microvilli, um, micropilli. I think that's the correct term. Anyway, these micro hairs that extend out and allow for them to be able to interact with any surface really. So the gecko hairs, because they're so concentrated, the uh, electrons are more gathered towards the tips of the hairs. And it is this slight attraction to the surface when it comes into contact with the surface that creates the stick. It creates the interaction, the attraction between uh, the surface and the hairs, the electrons that are in the hairs. Um, Gecko hairs are and feet are highly studied, and it's actually used in a lot of engineering to figure out ways that things can shape or conform to different surfaces. One of the things that we need to talk about is how a molecular shape and function go hand in hand. This goes back to one of the themes of biology, and that structure um, helps determine function. So a molecule's size and shape are key to its function. A molecule's shape is determined by the position of the atom's orbitals, or in other words, the positions of the atom's electrons. Molecular shape determines how biological molecules recognize and respond to each other. So, for example, opiates such as morphine um, are naturally produced, and naturally produced endorphins have similar effects because of the shape of their molecules. And so endorphins have this very complex carbon structure, circular carbon structure, and so does the morphine. And so the receptors that are on the cells in the brain, when it comes into contact with an endorphin, endorphins make you feel happy. It makes you feel happy. It also gets rid of some pain. Morphine, which we know what morphine does, it's a drug for pain. Also does that. It helps alleviate pain receptors in the brain. And so morphine actually mimics and copies what endorphins do naturally. So it is important to realize that every chemical reaction in the body, every chemical process that needs to occur is formed um, either the products that the body is creating or the breakdown of things that we need to digest is all facilitated by chemical reactions. So chemical reactions are the making and breaking of these chemical bonds. The starting molecules are called the reactants, and the resulting molecules are called the products. So it's like a recipe, right? So you need all the ingredients for your recipe. These are your reactants to create your product from that recipe. So two hydrogen molecules and oxygen molecules need to react together to create a water molecule. Now, there's a lot of complicated and complex chemical reactions that occur in the body. For example, photosynthesis is one of the most important chemical reactions, and you can see the equation here for photosynthesis. While you're not required to know this equation right now, we will come back to photosynthesis later on in the semester. But this is just a demo and show how unique you can have several molecules that can be complex in nature and produce products that are unique. And this is just showing you photosynthesis happening. The little bubbles are created underwater. It's important to know that all chemical reactions are reversible. We like to think that reactants produce a product, but really it can go the opposite way. You can take a product and break it back down into the reactants chemically. So you'll have a double arrow to indicate that things can be reversible chemically. And finally, it's important to know that a lot of reactions, sometimes a lot of biological processes need chemical equilibrium, like your body needs homeostasis to stay at a certain state. It's reached when forward and reverse reactions are the same. And so at equilibrium, the relative concentrations of reactants and products do not change. And with that, guys, that finishes chapter 2. Next, in chapter 3, we will review water and the properties of water.